I want you to consider two loading states for a very simple beam. Let's just imagine that this beam is some rectangular cross-section and it is simply supported at both ends. So the simple support means that it allows rotation but no displacement. And I have loaded this beam symmetrically about the center line, and I'll call this the center line right here, with a load P to the left of the center line, a load P to the right of the center line, and then the reactions, because it's symmetrically loaded about the center, are equal at each end of the beam. So if we were going to draw the shear diagram for this, we would start that shear diagram at P, and it would be constant, and then it would drop to 0, and then it would be constant, and then it would drop to minus P, and it would be constant, and then it would climb back up to 0 at the end of the beam. So that's a relatively straightforward shear diagram, and you'll notice that between the symmetric loads P, there is no shear. So let's go ahead and look at the bending moment diagram for this. What we find is that the bending moment, it ramps up, it is constant, and then it ramps back down to 0, as you would expect. So this is constant bending moment where there is no shear. This is a state of pure bending, and it is a unique stress state. Often when we have shear loads, we get variable bending moments. In this location where we had variable shears, you note that the bending moment changes as we move along the length of the beam, but where we had no shear, the bending moment was constant. So in the region where we have shear force, V, I'm going to need a shear pointing downward in order to keep this in equilibrium, and I'm going to have a bending moment. So I have a combination on this plane right here, I have a combination of shear and normal stress, and the normal stress would be compressive at the top side going to 0 and tension on the side below the neutral axis. When we move into the constant bending moment portion of the beam, all we have is bending stress. Our stress state is much simpler here. All we have is bending stress. So under this case right here, all we have is bending. All we have is bending, no shear. What if we look at a 3-point bend specimen where we load at the center of the beam? We still have reactions at each end. We have a reaction on the left side and a reaction on the right side, and those reactions are equal. We would find that under conditions where we have a centrally loaded beam with a load of magnitude 2P, that we have reactions of P and P on each end of the beam, of course. And if we were to look at the shear diagram, we would have a shear that would be constant. It would drop down at the center line, and it would be constant again over here. So it starts at V, ends at minus V, and then of course it goes back to 0 as well. So the bending moment in this particular case would vary continuously. Our bending moment would go up to a maximum and then back down to 0, as you can imagine. And so we have a constantly varying bending moment. And under those conditions, we get shear stresses throughout. So when we have a beam that has both shear and bending, as shown in figure 317 right here, then we have a moment that varies with X as we move along the beam. We also have a shear that's going to vary with X as we move along the beam. So if we take that little volume element out of the beam, which is shown over here in figure B, we note that the stress on the left-hand side is different than the stress on the right-hand side because the moment is changing as we move along the length of the beam. And because the moment is changing, if we take a little section through this, if we remove that section, which is what we're showing right down here, you will note that there is a net force F to the left, which is brought about by the integral of the change in the bending moment that occurred over this distance dx. And so that ends up with a net force. We take that my over I term and we integrate it from y1, which is the bottom of this segment, to y2, which is up at the top of that segment, and we multiply that by the section width of the beam B, and that would give us an area. And so we're missing that little area on that integral. But in order to resist that area, because the net force brought about by the change in moment, we are balancing that change in moment with this shear force tau. And that shear force times the cross-sectional area, tau, times the width B, times the length width of that dx has got to be equal to the change in the bending moment times y over I multiplied by the area over which it is acting. Well, the area is the width, and it's integrated from y1 to the outermost fiber, which we usually refer to as C. So, interestingly enough, if we the dm, the change in m, is not going to vary with y. So dA is simply b dy. So the change in moment is not going to vary with y. And so we can rewrite this as tau b equal to dm divided by dx now, the integral of y over I dA. So dm dx, that's simply equal to v. And so tau, that's how they get this equation right here. Tau is v over, they divide by b, and they remove the I from inside the integral. So tau is equal to v over IB times the integral from y1 to c of y dA. And that is the, first moment of the area. That's called the first moment of area. And so that becomes this really simple relationship. If we define that first moment of area by q is the first moment of area, then tau is equal to vq over IB. So if tau is equal to this vq over IB, so now if we take a look at that segment that we removed, remember that segment was up above the neutral axis. It was above the neutral axis by an amount y1, and we integrate all the way to the top of that segment. That's the height c. We had that variable moment that was occurring across the width of this thing. That thing is b. And on the bottom face, we have this tau, and we find that that tau, that shear stress, is vq over IB. Now, interestingly enough, is that if you go further up with y1 and create thinner and thinner slices, what ultimately must be true, if you look at the top of this beam, you have a really thin slice near the top of this beam. If you have a shear stress acting here, you would need a shear stress acting there. And so as the thickness here, dy, gets very, very small, the shear stress over that thickness has to go to zero. So shear is zero on the outer boundaries. That is why when you calculate what the shear stress is as a function of height y, you get this, for a rectangular cross-section beam, this beautiful parabolic curve, which shows that the shear stress has its maximum at the neutral axis. So the neutral axis, which is here, has the maximum shear, and it drops to zero at the outer boundary. The outermost boundaries, the bending stress is largest, and the shear stress is zero. At the middle, the neutral axis, the shear stress is maximum, and the bending stress is zero. This functional form, this parabolic functional form of the shear stress is shown here in equation 333. Now, depending upon the cross-section of the beam, you get different shapes. They're all somewhat parabolic, I have to say, but they vary with the cross-section of the beam over which they are acting. For rectangular cross-sections, tau max is 3 times the shear divided by 2a. You can get the shear from the shear diagram. For a hollow section, you get the maximum as 2v over a. For a structural I-beam, you will notice there is a step change in the shear stress as you move away from the flanges and get into the web of the beam. So the web has really large shear stresses. The maximum is given by this. For a circular cross section, you get that. And so there's a variation in the shear stress, but the maximum shear is always the center of the beam. For beams that are symmetric, it's always at the neutral axis at the geometric center of the beam. And so you have a competition between the location of maximum shear and the location of maximum bending stress. And that just takes you back to what we had talked about before, which is our Morse circle diagrams. So if we look carefully at our Morse circle diagrams, you would find that for a beam that had a variable load on it, so that we had both shear and bending, tau max is at the neutral axis, sigma max is at the outermost fibers. And so you would have to use your Morse circles, which have, as you move through the thickness of the beam, combinations of both sigma max and tau max, and you'd have to figure out, hey, where is the location of maximum shear? It could be, maximum shear could be along the neutral axis. I mean, we know that tau max is along the neutral axis, but what you have to see is whether or not tau max is greater than 1/2 sigma max, which you would get from Morse Morse circle. So this is kind of important because there is a competition between the locations of maximum shear stress, and it's important for those materials that fail in shear. There's a competition using your shear diagram from Morse circle where the maximum shear stress is going to be. And this plot in figure 319 shows the maximum shear stress as a location of L over H. Well, what the heck is L over H? Well, H is the height of the beam and L is the length of the beam. And now what we're doing is we're looking at locations Y away from the neutral axis. So we're looking at, for Y over C equal to 1, we're at the outermost fiber of the beam where we have the shear stress being equal to 0. Then as we move closer to the neutral axis, of course, the bending stress goes to 0. And so now what we have is the following. The maximum shear stress due to transverse shear, not bending, is always at the neutral axis. It's at Y equal to 0. And it is constant regardless of the length of the beam. But as the beam length gets large compared to the height, the maximum shear stress, which is calculated from this equation, occurs in the outermost fibers where the transverse shear is 0. That's just a Morse circle argument. But where L over H is 0.5 or less, an L over H of 0.5 or less is a very stubby beam, like so. So this is L and this is H. So for stubby beams, transverse shear is the dominant failure mechanism. For long, slender beams, bending is the dominant failure mechanism. So beyond L over H of 0.5, we are bending dominated. Below that, we are transverse shear. I want to go over an example in the book because this example helps you understand exactly why it's not always that easy. You have to do the calculations to sort things out. So this is a simply supported I-beam, and this I-beam is loaded asymmetrically with this 488-pound force 3 inches from the left side of the beam. And the beam is 12 inches long, so the H over A for this, or L over H, it's 4 times the height. And they want us to find out, okay, what are the locations that we need to worry about? What is the maximum shear stress due to transverse shear? What is the overall tau for combined bending and shear? So this geometry and actual shape geometry of an I-beam can be hard to analyze, and so they simplify it as these rectangular components. And when you look at this beam, you realize a couple of things. First, that the maximum bending stress is going to be at the top of the beam up here. My max shear is going to be here, but we have this huge drop-off in shear as we move from the web to the flange. And so we want to take a look at positions B and C, which are both sides just below the flange and just into the flange, and calculate what all the taus are for that as well. So in order to do that, we have to figure out what the I happens to be for this beam. That's relatively straightforward. We need to know the I because we need to know sigma bending stress, which is my over I. So we got to find the bending stress at all of these locations, Y, for A, B, C, and D. And we also have to find the transverse shear stress at all of those locations. Now, if you look at the shear and bending moment diagrams, which are shown right here, we notice that the bending moment varies continuously. There's no region where we don't have shear. And so we have to worry about transverse shear stresses everywhere in this beam. And that becomes a little bit problematic. But in order for us to find those transverse shear stresses, remember, we need to find the transverse shear stress is VQ over IB, where B is the width and Q is the first moment of area above the location we care about. And so when we look at this rectangular representation, we have to worry about at point A, we have all this area here above that we need to consider. At point B, we simply need to consider all of this stuff up here. Same thing at point A, and at point D, of course, we have no Q because we're all the way at the top of the beam. And so we have to sort out how we're going to calculate those things. And so we have these points A, B, C, and D, and we know that the Q for D is going to be 0. The Q for B is going to equal the Q for C because they're just inside and outside of the web. if we take that first moment of area, we can sort it out. We get 0.83 inches cubed. And QA, that is the area all the way above. First moment of all that area is 0.961. So those things are easy to calculate. They're a pain, but they're easy to calculate. And then you simply need to know what V is, what those Q's are, which we just calculated, what I happens to be. We needed that for the bending stress as well. And what the B is for each of those locations. So for location A, the B is the width of the thing. We'd have to figure out what that width was, which is actually given to us as 0.17 inches. All right, so we have that taken care of right there. Same thing at point B, the width is 0.17. As we go to point C, we have the whole width of this thing, so that's 2.33, and likewise at point D, it's 2.33, but we don't need to do this. We know it's going to be 0 because Q is 0, so just skip that step. What is the V? The V, well, we got to go to our shear diagram, and we see that our V at this location of maximum bending stress is the location we really care about, because it's either the bending or the transverse shear that's going to cause the largest shear stress in the sample. So we know that the V is 366. So we put that 366 in here. We've already calculated what the I was, and so we can easily calculate what the shear stresses are at A, it's 828, at B, it's 715, and at C, it's 52.2. PSI. All right, pretty straightforward. And it has this functional form, which is shown over here. That's how the shear stress, the transverse shear stress, varies with location along this I beam. We then calculate what the bending stresses happen to be at A, at B and C, and also at D. We know that at point A, which is the midsection, the bending stress has got to be 0. At B and C, the bending stresses are the same. So they are just the moment, which is recorded there. How do we get the moment? Well, we integrated the area, and we found the moment right. We integrated the shear to get the moment, and we found it to be 1098 inch-pounds. And so we have the bending moment. We have the distance to the location B at locations A, B, C, and D, and we find the bending stresses also from this. And then what we do at each of those locations, at the neutral axis, at positions B and C in and out, just outside the flange and just in the flange, and then at the topmost location, we use this Morse circle to help us find what the maximum shear stresses happen to be. And we find that in this particular situation that the maximum shear stress is actually at the neutral axis. So you may not have been able to predict that without having gone through the analysis.